To perform a load calculation for a pizza place, firstly determine the appliance loads. Let's assume the electric pizza oven is 50 kilowatts, the deep fryer is 20 kilowatts, the dough mixer is 10 kilowatts, refrigeration is 15 kilowatts, and the ventilation system is 10 kilowatts. Secondly, calculate the total appliance load by summing these values. Total appliance load equals 50 kilowatts plus 20 kilowatts plus 10 kilowatts plus 15 kilowatts plus 10 kilowatts, which equals 105 kilowatts. Thirdly, apply the diversity factor. According to National Electrical Code Table 220.83, the diversity factor for restaurants is 0.7. Multiply the total appliance load by this diversity factor to obtain the reduced appliance load. Reduced appliance load equals 105 kilowatts times 0.7, which equals 73.5 kilowatts. Fourthly, calculate the service load. Multiply the reduced appliance load by the non-continuous load factor, which is 0.8. Service load equals 73.5 kilowatts times 0.8, which equals 58.8 kilowatts. Concerning metering equipment, you will need to change the metering equipment, including the meter socket, and service entrance conductors to accommodate the increased load. Regarding service upgrading, you will need to upgrade the wire and panel on the first floor to 200 amps. National Electrical Code 220.2 B1 states that continuous loads must not exceed 80% of the ampacity of the branch circuit or service conductors. To determine the appropriate panel size, convert the service load from kilowatts to amps. 58.8 kilowatts divided by 208 volts equals 282.7 amps. A 200 amp panel is not adequate because it violates the 80% rule. You need a panel that provides at least 282.7 amps divided by 0.8 equals 353.4 amps. A 400 amp service is a better choice to provide ample power and meet code requirement. The closest standard panel size that meets the 80% rule is a 400 amp panel because 400 amps times 0.8 equals 320 amps. Always ensure that the electrical system is designed and installed to meet all applicable codes and standards, including the National Electrical Code. Consider providing additional circuits and capacity for future expansion. Obtain necessary permits and inspections from local authorities. Also, install a ground fault circuit interrupter for added safety. Load calculations are critical for ensuring safety and compliance with electrical codes. Firstly, identify all electrical loads. Accurately catalog every electrical appliance, device, and system that will draw power. This includes lighting, heating, cooling, cooking equipment, refrigeration units, and any specialized machinery. Each load should be specified with its power requirements, usually in watts or kilowatts, and its voltage. Secondly, distinguish between continuous and non-continuous loads. The National Electrical Code defines a continuous load as one that operates for 3 hours or more at a time. Continuous loads require special consideration because they can put sustained stress on the electrical system. Non-continuous loads, on the other hand, operate for shorter durations. Thirdly, apply demand factors. Demand factors account for the likelihood that not all loads will operate simultaneously at their maximum capacity. These factors are typically derived from historical data or industry standards and are applied to reduce the calculated load, preventing overestimation. The specific demand factors can be found in the National Electrical Code. Fourthly, calculate the total connected load. This is the sum of all individual loads without applying any demand factors. It represents the maximum possible load if everything were to operate at once. Fifthly, calculate the demand load. This is the total connected load multiplied by the appropriate demand factors. The demand load represents a more realistic estimate of the load that the electrical system will need to support under normal operating conditions. Sixthly, consider voltage drop. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To mitigate voltage drop, conductors must be sized appropriately based on their length, ampacity, and the load they serve. Seventhly, size the service entrance. The service entrance must be sized to handle the calculated demand load plus any additional capacity needed for future expansion. The service entrance includes the service conductors, the service disconnect, and the overcurrent protection devices. Eighthly, select appropriate overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the electrical system from overloads and short circuits. These devices must be sized appropriately to coordinate with the ampacity of the conductors they protect. Ninthly, ensure proper grounding. Grounding is essential for safety and helps to prevent electrical shock. The grounding system must be installed in accordance with the National Electrical Code and must provide a low impedance path for fault current to return to the source. Tenthly, verify compliance with codes and standards. Ensure that the entire electrical system complies with all applicable codes and standards, including the National Electrical Code and any local regulations. A qualified electrical engineer or electrician should review the design and installation to ensure compliance. Upgrading a service involves several key steps to ensure safety, reliability, and compliance with electrical codes. Firstly, assess the existing electrical system. A thorough evaluation of the current electrical system is necessary to determine its capacity, condition, and compliance with existing codes. This includes inspecting the service entrance, distribution panels, wiring, and grounding system. The assessment should identify any deficiencies, such as undersized conductors, overloaded circuits, or outdated equipment. Secondly, determine the new load requirements. Accurately calculate the new load requirements based on the anticipated electrical usage. This involves identifying all electrical appliances, devices, and systems that will draw power and determining their power requirements. Consider both continuous and non-continuous loads, as well as any future expansion needs. Thirdly, select the appropriate service size. Based on the load calculation, select a service size that can adequately handle the demand load plus any additional capacity for future growth. The service size is typically specified in amps and volts and must comply with the National Electrical Code and local regulations. Fourthly, upgrade the service entrance. The service entrance includes the service conductors, the service disconnect, and the metering equipment. These components must be upgraded to match the new service size. The service conductors must be sized appropriately to handle the increased current, and the service disconnect must have sufficient ampacity to interrupt the entire load. Fifthly, replace or upgrade the distribution panels. Distribution panels, also known as breaker boxes, distribute power to individual circuits throughout the building. If the existing panels are outdated, undersized, or in poor condition, they should be replaced or upgraded to accommodate the new load requirements. The panels must have sufficient capacity for the number of circuits needed and must comply with the National Electrical Code. Sixthly, install new branch circuits. New branch circuits may be required to serve additional loads or to replace existing circuits that are no longer adequate. Branch circuits must be sized appropriately for the loads they serve and must be protected by overcurrent devices such as circuit breakers or fuses. Seventhly, upgrade the grounding system. A properly installed grounding system is essential for safety and helps to prevent electrical shock. The grounding system should be upgraded to ensure that it can effectively handle fault currents and provide a low impedance path for current to return to the source. Eighthly, test and inspect the system. After the service upgrade is complete, the entire electrical system should be thoroughly tested and inspected to ensure that it is functioning properly and complies with all applicable codes and standards. This includes testing the grounding system, checking the voltage and current levels, and verifying the operation of all overcurrent devices. Ninthly, obtain necessary permits and inspections. Obtain all necessary permits from local authorities before starting the service upgrade. Schedule inspections at various stages of the project to ensure compliance with codes and regulations. Tenthly, document the changes. Keep detailed records of all changes made to the electrical system, including wiring diagrams, load calculations, and inspection reports. This documentation will be helpful for future maintenance and troubleshooting. When metering equipment is modified or upgraded, Several key considerations must be addressed to ensure accurate billing, safety, and compliance with regulations. Firstly, select the appropriate meter. The meter must be selected based on the expected load and the voltage and current characteristics of the electrical service. Digital meters are generally preferred for their accuracy and ability to provide detailed data. Secondly, ensure proper meter socket compatibility. The meter socket must be compatible with the meter and must be rated for the appropriate voltage and current. The socket should be inspected for any signs of damage or corrosion before installing the new meter. Thirdly, verify meter accuracy. The meter should be calibrated and tested for accuracy before installation. This can be done by a qualified meter technician using specialized testing equipment. Fourthly, install surge protection. Surge protection devices should be installed to protect the meter and other electrical equipment from voltage spikes and surges. These devices can help to prevent damage and extend the life of the equipment. Fifthly, ensure proper grounding. The meter and meter socket must be properly grounded to ensure safety and prevent electrical shock. The grounding system should be inspected to verify that it meets all applicable codes and standards. Sixthly, seal the meter. The meter should be sealed to prevent tampering and ensure accurate billing. The seal should be installed by a qualified technician and should be inspected regularly. Seventhly, document the meter installation. Detailed records of the meter installation, including the meter serial number, installation date, and location, should be maintained. This information will be helpful for future maintenance and troubleshooting. Eighthly, comply with utility requirements. The meter installation must comply with all requirements of the local utility company. This may include obtaining approval from the utility before installing the meter and following specific procedures for connecting the meter to the electrical service. Ninthly, consider advanced metering infrastructure. Advanced metering infrastructure (OMI) includes smart meters and communication networks that allow for remote meter reading and monitoring. AMI can provide valuable data for managing energy consumption and improving grid reliability. Tenthly, provide customer education. Customers should be educated about the new meter and how it works. This includes explaining how to read the meter and how to report any problems or concerns.